Welcome. I'm walking you through something every refinery and petrochemical team lives with, but doesn't always name clearly: severe operating conditions. Not abstract theory. The real pressures, temperatures, environments, and reaction chemistry that quietly or suddenly destroy equipment. Think of a plant as a system that only stays healthy inside a design envelope. Step outside that envelope: too high, too low, too aggressive, too reactive, and the metal starts paying the bill. Today we'll look at 4 families of severity: pressure-based, temperature-based, environment-based, and reaction-based. Watch how each one attacks components differently. Start with pressure. What this gauge animation shows is the load the wall actually feels. Overpressure stretches the vessel toward yield, then plastic deformation, then rupture if relief doesn't catch it. Vacuum is the silent twin: thin-walled tanks and large diameter lines can buckle inward when steam collapses or pumps pull harder than the design allows. And then there's cycling. Every startup, every swing, every water hammer or surge event puts another fatigue tick on nozzles, bellows, and weld toes. In practice, we don't just ask, "What's the design pressure?" We ask how often we push it, and how fast the spikes arrive. Now, temperature. Heat isn't one problem, it's several. Sustained high-temperature underload is the creep story. The metal slowly stretches even below yield, and fired heater tubes, reformer pigtails, and hot wall reactors are classic victims. Thermal shock is the opposite end: cold feed into a hot line, or quench water on a hot surface, and that gradient can crack brittle materials in a single event. Low-temperature service brings embrittlement. Carbon steels lose toughness, and a pressure excursion that would be fine at ambient becomes a brittle fracture risk below the minimum safe operating temperature. Hotspots from flame impingement or maldistribution create local overheating while the average reading still looks acceptable. The key takeaway: temperature damage is about gradients and time, not just the number on the board. Environment-based severity is chemistry meeting metal. Sour service: hydrogen sulfide drives blistering, hydrogen-induced cracking, and sulfide stress cracking in susceptible steels. Chlorides love austenitic stainless and open the door to stress corrosion cracking under tensile stress. Acidic condensates, wet CO2, amine carryover, caustic, and polythionic acids each have their preferred attack zones, especially where condensation, stagnation, or underdeposit chemistry concentrates the aggressor. External environments matter too: coastal salt air, polluted atmospheres, and wet soil under tank bottoms. In practice, the worst environments are often local: dead legs, low points, under insulation, while the bulk stream looks mild. Reaction-based conditions are where the process itself becomes the weapon. High-temperature sulfidation thins carbon and low-alloy steels in sulfur-bearing streams. Carburization embrittles furnace tubes when carbon from the process diffuses into the metal. High-temperature hydrogen attack (HTHA) degrades carbon steel in hot hydrogen service by forming methane at grain boundaries. Exothermic runaway, hot regeneration cycles, and coke or scale deposits create reaction hotspots that push local metal temperatures far beyond the control room average. Fouling isn't just an efficiency issue, it changes heat transfer and can drive the metal into a damage regime the designer never intended. Here's the part operators feel in the field: these families rarely act alone. High pressure plus low temperature is a brittle fracture trap. High temperature plus hydrogen is an HTHA trap. Chlorides plus residual tensile stress plus heat is classic chloride SCC. A process upset can stack 3 severities in minutes. So when we assess integrity, we don't list conditions in isolation, we map how they combine at each piece of equipment. So what do we do with that? First, know the credible severe conditions for every critical component, design limits, upset scenarios, and the environments that actually occur, not just the ones on the datasheet. Second, control the factors you can: relief and vacuum protection, temperature excursions, chemistry envelopes, and startup shutdown discipline. Third, inspect where severity concentrates: welds, nozzles, dead legs, hotspots, soil-side tank bottoms, with methods matched to the damage you expect. Recognize the condition early. Stay inside the envelope. Verify with purpose. That wraps this session on severe operating conditions in petrochemical and refining plants. This briefing was prepared by Jaresa Consultation Services, helping integrity, inspection, and operations teams turn operating severity into safer, more reliable decisions.